A motorboat whose speed in still water is 2.6 meters per second must aim upstream at an angle of 28.5 degrees in order to travel directly across the stream. So the first question is, what is the speed of the current? The second question is, what is the resultant speed of the boat with respect to the shore? Now first, let's take a look at the picture. This is a simple diagram for this question. As you can see, the initial speed of a motorboat is 2.6 meters per second, and the angle is 28.5 degrees. Now let's take a look at the first question. From this picture, we can know that tangent 28.5 degrees is equals to the initial speed, the motorboat's initial speed divided by the speed of current. So we can know that we can know this formula, and then we can now calculate the speed of current is that tangent 28.5 degrees times 2.6 meters per second. So the answer for first question is 1.41 meters per second. Now for the second question, we can know the velocity of BW is the speed of the boat with respect to the shore. So we can know from this picture is that cosine 28.5 degrees is equals to initial speed divided to velocity BW. So now we can know that cosine 28.5 degrees is equals to 2.6 meters per second divided by speed. So the speed of the boat with respect to the shore is cosine 28.5 degrees times 2.6 meters per second. So the final answer is 2.28 meters per second. Now let's take a look at this question. A boat whose speed in still water is 1.7 meters per second must cross a 260 meter wide river and arrive at a point 110 meters upstream from where it starts. To do so, the pilot must head the boat at a 55-degree upstream angle. So the question is, what is the speed of the river's current? Now let's take a look at the picture for this question. Okay. First, we need to know the velocity of y-axis. So because we know the angle is 45 degrees, so we can know that sine 45 degrees equals to the initial velocity, the initial velocity of y-axis divided by the initial velocity, which is 1.7 meters per second. So we can calculate that initial velocity of y-axis is equals to 1.2 meters per second. Now we need to calculate the initial velocity of x-axis. So we can also use the Pythagoras theory, and so cosine 45 degrees is equals to initial velocity of x-axis divided by 1.7 meters per second plus the velocity of water, and we can have the result of initial velocity of x-axis is equals to 1.2 meters per second minus the velocity of water, because the speed of initial velocity of x-axis is this direct direction, and the velocity of water is opposite of the initial velocity of x-axis, so we have to minus the initial velocity of water. Now you can use the distance for the distance of y-axis divided by the speed of the initial velocity of y-axis. Then we can calculate that the time the boat cost, which is 2.7 seconds. Finally, we can know that the distance of x-axis is equals to the initial velocity of x-axis, which is this one, times the time. So we can get this. And finally, we calculate the velocity of water, which is minus 39.45 meters per second. So the river current, which is the answer, is 39.54 meters per second. Let's look at this question. A rescue plane wants to drop supplies to isolated mountain climbers on a rocky ridge 235 meters below. The plane is traveling horizontally with a speed of 250 kilometers per hour, which is 69.4 meters per second. So the first question is, how far in advance of the recipient horizontal distance must the goods be dropped? And let's take a look at the first diagram. So, as it's given, if the y0 equals to 0 meter, then the y is minus 235 meters. And the initial velocity of x-axis is already given, which is 69.4 meters. So what is occurs in the problem A is that this x-axis distance. Now let's take a look at the solutions. First, we need to figure out the time that it cost to the supplies to drop to the peoples. We use this formula to calculate the time, which is 6.925 seconds. See, y is minus 235 meters and y0 is 0 because there is no initial velocity of y-axis, so it is 0 meters, and the gravity is minus 9.8 meters per second squared, and so this is why we can get this number. Now, if we know the time, then we can calculate the distance of x-axis, because we know the velocity of initial x-axis. We just need to use initial velocity of x-axis times time, which is 481 meters. This is our final answer. And let's take a look at the second question. Suppose instead that the plane released the splice a horizontal distance of 425 meters in advance of the mountain climbers. What vertical velocity should the splice be given so that they arrive precisely at the climber's position? Now let's take a look at the diagram for second question. Still, the y0 is 0 meter and the y is minus 235 meters. But now we still know that the initial velocity of x-axis is 69.4 meters per second. But the distance is given, which is 425 meters. Now, what we want to know is that the initial velocity of y-axis and if it is upward or downward. Now let's take a look at solutions. Still like the first questions, we need to figure out the time. So now the distance of x-axis is given and the velocity of x-axis is given. So it is easy to calculate the time, which is 6.124 seconds. Now we still use this formula to calculate the initial velocity of y-axis, and we can know that the initial velocity of y-axis is minus 8.39 meters per second. Because it is negative, so the direction of this velocity is downward. Now let's take a look at the final questions. With what speed did the splice land in the later case? Now, because we know the initial velocity of y-axis and we know the initial velocity of x-axis, so it is easy to calculate the final velocity of the splice. First, we need to calculate the final velocity of y-axis, so we will use this formula. T is occurred in last questions, so the final velocity of y-axis is 68.385 meters per second. And now, because we know the velocity of x-axis is remain same, so the final velocity of x-axis is same as the initial velocity of x-axis, which is 69.4 meters per second, and we just know that the final velocity of y-axis is 68.385 meters per second. So we can easily calculate the final velocity of the splice, which is 97.43 meters per second. Here it comes to the last questions. Determine how much farther a person can jump on the moon as compared to the Earth if the takeoff speed and angle are the same. Here's a little tip. The acceleration due to gravity on the moon is 1/6 what it is on Earth. So from the question, we can know that the velocity on the Earth is equals to the velocity on the moon, and the angle of the on the Earth is equals to the angle on the moon. And the gravity of it, as we all know, is 9.8 meters per second squared. From the tips, we can know that gravity on the moon is 1/6 what is on the Earth, so it is 94 divided by 30 meters per second squared. We can use this formula to calculate the range. So the range is the velocity squared times sine theta divided by g. So on the Earth, the range is, because the velocity remains same on two planets, so we assume that the velocity is very zero, and it is same for sine theta, so we just assume the angle is both sine and theta. Now we can calculate the both of their range. First, the range on the Earth is v0 squared times sine theta divided by 9.8, and on the moon it is v0 squared times sine theta divided by this, which is v0 squared times sine theta times 30 divided by 49. For last step, we just need to use the range on moon to divide. You use range on E to divide the range on moon, which is this, and we can cross out the same, and the final result is 6. So it is 6 times farther.